class. Okay, so topic for this lecture, we're going to talk about the specific heat of a gas. So earlier we talked about specific heat for a solid or a liquid. You know, Cm delta T, where this is the specific heat. M is the mass and delta T is a change in temperature. So if you add heat to an object, you're going to change the temperature. And yeah, this formula only applied for solids and liquids. It did not apply for gases. And the reason why, let's look at a couple of examples to explain why that formula could not be applied to a gas. Let's say we have a situation, I'm going to draw, let's move that over. So we have two cases. Say one, we just have a cylinder with a fixed volume. Let's keep the volume in the two the same, at least initially. So we have a gas in here, and we have a gas in here. Say these are at the same volume, except this one has a movable piston. So let's say we add heat to this gas. Where is this energy going to go? Where it has nowhere else to go except into the gas, and it's going to cause a temperature change. It's going to cause a large temperature change, relatively large. Now, say we take the same amount of heat and we apply it to this gas. Well, in this gas, what happens to a gas when you heat it up? So we're adding heat, we're increasing its temperature, but what happens, when you increase temperature of a gas, it wants to expand. And now it has a movable piston, it can expand, but in doing so, it's got to lift this piston up. At the very least, it has to lift the piston. Maybe the piston has some resistance. Maybe it's going to push something. So other than just its mass it's lifting up, maybe it's going to be pushing something. But anyways, it's going to be doing work on the environment. So here, let's say we add 1,000 joules to this first gas. All the energy that we put in here is going to increasing the temperature of the gas. Here, if we put 1,000 joules in, some of it's going to go into heating the gas, but some of it's going to be converted into work. So we're going to get a smaller temperature change here. And so we have the same amount of gas in both cases. We're putting the same Q in there, but we're getting different temperature changes because they're doing so under different circumstances. Here we have a constant volume, here we do not. And so the result is going to be different. So we can't have this simple formula here for gases because it depends on how the gas is going to respond to this addition of heat. So we have to consider a couple cases here. We are going to write down a formula though, kind of inspired by this one. Say Q is the heat added. Now we're going to have a specific heat for a gas, which maybe you can't tell the difference. That's a lowercase c. For some reason, we use a capital C for the specific heat of a gas. Now instead of the mass of the gas, let's measure, or like here we have a solid, so naturally we'd measure that in mass. But for the amount of a gas, let's say number of moles. Okay, so this is our basic formula for the specific heat of a gas. However, we have we're going to look at two kind of special cases. Let's say we have that first example where we just have a gas in a fixed volume. So it's just in this cylinder. We add heat. And we'd say that this would be the specific heat at a constant volume, so we call that CV. So this is a basic formula, but the C, we have to indicate like what conditions are we like adding this heat under. Like, is it a constant volume? The other one we're going to look at is CP. If we add heat and the gas expands at a constant pressure. So let's look at this one first, though. So here we have heat added. This was the specific heat at a constant volume, and that's N delta T. So let's write down the first law of thermodynamics. Delta U is Q minus W. All right. Now, in this case, since we're at a constant volume, W is 0. So CV implies that W equals 0. And so Q is equal to delta U. And I'm going to write down a few other things over on the side. Or for a monatomic gas, we have 3/2 nRT, and for a diatomic gas, 5/2. And then for a diatomic gas, 5/2. Okay, so again, we talked about specific heat of a gas. We need to know if it's occurring at a constant volume or at a constant pressure. We also need to know what type of gas it is. So basically what we're going to end up with for specific heat of a gas. We're going to have a table where we're going to have like all the different conditions. And it's on the equation sheet. I just want to look up how I organized it. Yeah, we did monatomic and diatomic. Wasn't sure if we wanted to put like CV, CP, and then monatomic or diatomic, or the other way around. Just want to be consistent. With what's in the equation sheet. And then we have CV and CP. So basically we want to fill out this table. That's our goal for this lecture, basically. So let's say we have let's figure out this one. We're going to figure out this column first, but right now let's say we have a monatomic gas. Then delta U is 3/2 nR delta T. And let's just rewrite this a little bit. Let's call this 3/2 R times N delta T. Why do we rewrite it? Well, this is our basic formula where we have Q equals CV times N delta T. Here, this is CV, the specific heat for constant volume for a monatomic gas. This is 3/2 R. So you can see by just comparing, what we got from the first law of thermodynamics with the basic equation and just rewriting a little bit, we can see that CV is 3/2 R. Okay, now let's consider the diatomic case. No, that's basically the same thing, but we just have 5/2. Delta U would be 5/2. So, let's just. So for a diatomic gas, the specific heat at constant volume is 5/2 R. Okay, and again, you don't need to memorize these things, or you don't have to derive them every time you come across them. You will have those on the equation sheet, but now let's look at this other case where we have the gas expanding at a constant pressure. So again, let's look at the first law of thermodynamics. Let's solve for Q. So Q equals delta U plus W. We can write it that way. And remember the work, we're doing this at a constant pressure, so remember work for an isobaric process, work is P delta V. Okay. Now, we need one more thing here. We also need the ideal gas law. So again, because, well, let's look at this. Here, we have a constant pressure in this case. So P is constant, N and R are constant. Our only variables are V and T. So I think I'll write down the answer, but then I'll kind of show it off to the side. So P delta V, that's going to be NR delta T. So again, just to show that, P delta V, that would be P times V final minus P times V initial. And PV final, that would be nRT final minus nRT initial. And we factor out the nR's, we have nR times delta T. So, yeah, so I want to work that off to the side. And now let's start with the monatomic case. Here, let me do these both at once. So for a monatomic case, delta U is 3/2 nR delta T, and P delta V, that was nR delta T. So if we put this together, we have 5/2 nR delta T, or 5/2 R times N delta T. So again, this is the specific heat at constant pressure for a monatomic gas. So we use the monatomic, we use 3/2. But because of that contribution to work, we had 5/2. And so again, we get a bigger specific heat here, which again, we expected. Because a bigger specific heat means a smaller temperature change. And this is a case where we're adding heat and the gas is expanding and doing work. So we're not converting all the heat we had that we added into a change in temperature. Some of it's going to work. So we should expect a smaller change. And finally, we have to fill out this diatomic case. The only difference here is we replace 3/2 with 5/2. And then 5/2 plus 1 is 7/2. So we get 7/2 R over here. So we filled out this table for the specific heat of a gas. So again, it depends on the conditions that heat is being added. You know, what's the gas doing when we're adding the heat? Is it expanding at a constant volume or a constant pressure? And we also have to consider what type of gas, monatomic or diatomic. And again, these values hold up at normal conditions, like normal room temperature type of gas. If we change that, these numbers could change for diatomic. But, okay. So that's the main goal, is filling out that table. But I wanted to find something else. We define this number gamma as this ratio Cp over Cv. So we define that this is just a number. The specific heat of a gas, you know, the units we'd have joules over moles times Kelvin. But again, they have the same unit, so gamma is just a number, and it depends on what type of gas. Let's say we have a monatomic gas. Then gamma would be Cp over Cv, so this would be 5/2 R over 3/2 r, which would just be 5/3. If we have a diatomic gas, we'd have gamma is 7/2 r divided by 5/2 r. So that would be 7/5. So gamma, I think that's in the notes as well. Yeah, 5/3 for a monatomic gas, 7/5 for a diatomic gas. And again, that's going to come up later, this gamma. I kind of mentioned it before. For an adiabatic process, PV to the gamma is a constant. We'll talk more about that later. But for now, I kind of want to mention what that gamma actually means. So we're talking about PV diagrams. I just mentioned this, so we can get an idea of what the graph would look like. But now at least we have some idea of what gamma is. We don't really know why this is true right now, but yeah, we'll just take that as a given for now. Okay, so specific heat of a gas, a bit more complicated than for solids and liquids. But that'll be it for this one.